Hello, boys and girls, and welcome to another episode of your favorite algorithm channel. My name is Ryan Powers, and today I'm going to be taking you through LeetCode 33, Search in Rotated Sorted Array. So let's introduce the problem. Suppose an array sorted in ascending order is rotated at some pivot unknown to you beforehand. So here's an example of what the array would look like beforehand, and then what it might become. So I think the important point to note here is that we're basically chopping off some portion of the front half of the array and appending it onto the end. So the rotated point is going to be right here around 7, right? So it was 0, 1, 2, 4, 5, 6, 7, and now it's become 4, 5, 6, 7, 0, 1, 2. So that's the important bit. That is the rotated portion of the array. So you're given a target value to search. If found in the array, return the index, otherwise return -1. So we're going to search through the array. We're given a number to look for. If we find it, let's return the index. If not, we'll return -1. So you may assume no duplicates exist in the array, which is awesome. And let's see, your algorithm's runtime complexity must be in the order of log n. So what does that mean? Well, that means that we should be eliminating half of our answers at each iteration. So that's kind of a hint for you as to what kind of mindset should you be in when solving this problem. So let's look at some solution examples. So here's an array, 4, 5, 6, 7, 0, 1, 2, target is 0, the output should be 4, right? So we should be returning this index where we find 0. And then here in this other one, where we're looking for 3 and it doesn't exist, we're returning -1. So I think this is actually a really, really cool problem. It should be, it should illuminate some algorithm strategies for you and maybe different ways to think about doing some kind of log n operation. But anyways, as always, I suggest that you try to solve the problem on your own first. And if you get stuck or you just want to see how I solved it, then come and check out the video. Otherwise, if you're ready to get started, come with me to the whiteboard. What's the strategy we're going to use to solve this problem? So we need to find our value in log n time. And that means we need to eliminate half of our answers at every iteration. Well, that should be a big flashing light to you that we should be using binary search to solve this problem. Well, I have so on the screen here, I have 2 arrays. So I have an array that's rotated around 9. So why is it rotated around 9? Well, you could see that if we took 1, 2, and 3, used to be right here, we basically took those numbers off and appended them to the end of our array. So our array is rotated around the point of 9. And on the bottom here, I just have a regular sorted array. So I first want to go through a round of using binary search to find our target value in our array. And then we'll talk about how we might be able to use this strategy to solve our overall problem, right? So we'll have a pointer to our low value and our high value. And we're going to just take the middle value of this array, which is 5, right? And let's say the target we're looking for is 8. Well, at each iteration, we're going to ask ourselves first, does our value equal our target? It does not. And then if our value is less than our target, well, then we know we can eliminate all of the answers to the left of 5, right? Because everything to the left of 5 is less than the target. So if our current value is less than the target, our answer is not going to be over there, right? So we'll ask ourselves, is our current value less than our target? So this is our current value. Is it less than our target? Yes, it is. So we can eliminate all these answers. So we'll take this pointer here and we'll move it up to here. So now we know that we can just look between 5 and 9 for our answer. So we'll take the middle value, which is 7. We'll compare it to our target. Are they equal? No, they are not. Is 7 less than 8? Yes, it is. So we know we can eliminate all of these answers. So we'll do that, and we'll take this pointer here, and we'll move it up to 7, because we know now that our answer is between 7 and 9. So at the next iteration, we're going to look at our middle value, and we're going to say, is it equal to our target? Well, yes, it is, right? So we found our answer. So you can see that it would be very easy for us to use this strategy to find a number in a sorted array. So how could we apply this strategy to this rotated array up here? Because it's not sorted in ascending order, right? I mean, it's kind of sorted in ascending order. This portion is sorted in ascending order, and this portion is sorted in ascending order. But how would we use this strategy on the entire array overall? Well, we can all agree that we could use binary search on this portion of the array if we knew that our answer was over there. And we also know that we can use binary search on this portion of the array if we knew our answer was over here. So the key to the problem is finding this rotation point. Now, you might be thinking, hey, I could just iterate through the array, check for the first decreasing value, and there's my rotation point. But that takes our problem from a log n solution to an n solution. And we can't do that. We're supposed to find it in log n time. So that means we need to find this rotation point in log n time. So we need to use binary search to find this rotation point. So what did we do down here? Well, all we did was look at our current value and say, what half of the answers on the side of the value I'm looking at can I eliminate, right? So we said, oh, 5 is less than 8. So that means anything less than 5 is not going to be our answer. Well, we need to figure out how we can do the same thing up here, right? So let's make a little bit more space for ourselves and talk about how we could use binary search to find our rotation point. Because if we find the rotation point, then we know that, that we can solve this problem, because we can just use binary search on the sorted portion of the array to find our answer. So what's true about our rotation point that's not true about any other number? Well, it's the maximum point in our array, so we know that it's both greater than the value on its left and the value on its right, right? It's the only value in the array that is like that. So that is our exit case. So let's write that down. So if the current value is greater than right, and the current value is greater than left, well, we're done, right? We're done. And so what else can we say about these numbers? Well, how do we know that when we land on a number that we're on the left side and we could eliminate everything to the left of that number? Or how do we know that we're on the right side and we can eliminate everything to the right of that number? Well, if we look at this first value here, 4, what is 4? Well, 4 is the minimum value of all of the numbers to the left side of our pivot point or our rotation point. And what is 3 over here? Well, 3 is the maximum value of all the values to the right of our rotation point. So if at every iteration we land on a number, say we land on 6, we can just compare it to the first value in our array. And we can say, is our current value greater than or equal to the first value in our array? If that's true, then we know we can eliminate all of these values to the left, and we need to search right. So we need to go right. And if that's not true, well, then that means that we need to go to our left, right? So using this strategy, we should be able to find our peak. So let's go through one iteration of finding our peak just to prove to ourselves that this will work. All right, so we'll set our bounds, we'll set our high pointer, or our low pointer and our high pointer, and we'll start looking at the middle value. We'll check to see, is it greater than the value on its left? Yes, it is. Is it greater than the value on its right? No, it's not. So that means that it's not our peak. So is the current value greater than or equal to 0? Well, yes, it is. So that means we can eliminate all the values to the right. So we'll take this low pointer and we'll move it up to 8. So now we know our answer lies between these 2 points. So we'll take the middle value, which is 1, and we'll compare it to the value on its left. Is it greater than the value on its or on its right? Is it greater than the value on its right? No, it's not. So we know that this is not our peak. So we'll check to see, is the current value greater than or equal to the first value in the array? It's not. So that means we can eliminate all the answers to the right of this value. So we'll take our high pointer here and we'll move it up to the current value that we're on. And now we're going to take the middle value between these 2 points. And we'll check to see, is the current value greater than the value to its right? It is. Is the current value greater to the value on its left? It is. So we're done. So we've found our peak, right? So we now know that we can find our peak in log n time, and we also know that we can find any value to in a sorted array in log n time. So now that we've found our peak, we can just say that if our target was 3, well, then we know we need to do binary search on this half of the array. And if our value was something like 6, well, then we know that we would need to do binary search on this portion of the array. So combining these two sub-problems, finding the peak first in log n time, and then doing the binary search in log n time, we should be able to come to our answer. So let's go through one round of combining these strategies to solve the problem before we go ahead and see what this problem looks like in code. On the screen here, I have a representation of the two sub-problems that we're going to use to solve this greater problem. So the two sub-problems are find peak and binary search. So let's just go through one round of pulling these two problems together to solve this overall problem of finding a target in a sorted or in a rotated array, or doing search in a rotated array, just to get an idea of how we were going to tie these two sub-problems together. So first we'll initialize our pointers and we'll select our midpoint at 9, and let's do a target of 5. So we're searching for 5 in this rotated array. So the first thing we need to do is find our peak. So we'll use our find peak function, and at each iteration we're going to do these 3 things. We're going to check to see is the value on my left and my right, am I greater than both these values? If I'm not, then I need to decide, do I need to go left or do I need to go right? So first we'll check to see is this current value greater than both of the values to either side? Well, it's not. So then we'll check to see is this current value, is it greater than or equal to the first value in the array? Well, it is. So we know that we can eliminate all the answers to the left. So we'll move our pointer and we'll move our midpoint to the middle, and we'll re-evaluate this loop. We'll check to see if the current value is greater to the two values to either side. It's not. It's also not greater than or equal to the first item in the array. So we'll reset high to be this value, and we'll refine the midpoint between these two pointers. So we'll now check to see if the this midpoint is greater than both values to its right, or its left and its right. Well, it is. So we know we've found our peak, right? So now we just need to decide which side of the peak do we need to search on. So we can easily accomplish that by looking at our target and checking to see if it's greater than or equal to the first item in the array. Well, it is greater than or equal to the first item in the array, so we know that it's part of this group of numbers on the left side of the peak. So we can reset our pointers and find the midpoint, and we can start doing binary search. So we'll move our pointer over to binary search, and we'll check to see, is the midpoint equal to the target? Well, it's not. Is the midpoint less than the target? It's not. The midpoint is higher than the target, so we know we can eliminate all answers to the right of 7. And we'll refine our midpoint, and since we're going to be flooring our midpoint, we'll go to the value lower, so the lower value, and we'll check to see, is this midpoint equal to the target? Well, it is equal to the target, right? So we've found our problem. So this is kind of how we're going to tie these two subproblems together to code out or solve this this problem of finding or searching for a value in a rotated array. So let's now that we know how to solve this problem, let's see what it looks like in code. On the screen here, I have our two helper functions, find peak and binary search, as well as our search function that we're going to use to implement the to combine these two subproblems into formulating our answer. So let's first combine the two subproblems. So we'll create a variable peak, and in that variable, we will store the result of calling find peak, passing in our array. So that's going to give us our peak value, or the max value in the array. And after we found that, well, we want to do binary search, right? But what half do we want to do our binary search on? Well, we'll look at the first index in that array, and if that is greater than our target value, then we know that our answer lies to the right side of our peak. So we want to do binary search, passing in our array and the target, and we want to start looking at we want to put our low index at peak +1. And if that's not the case, then we want to do binary search on the left side of the peak. So we'll do binary search, passing in the array and the target, and we want to start at the 0 index, and we want to go all the way until peak +1. So this kind of takes care of the higher level logic of our problem, combining our two subproblems. So now we just need to implement the logic for our two helper functions. So we'll start with find peak, and we need to define a midpoint. So we'll let mid be equal to math.floor of combining our high plus our low and dividing it by 2. So that's going to give us our midpoint. And then what's our exit case? Well, our exit case is that the number we land on is greater than both the number on its left and its right. So we'll say that if the current index -1, if that is greater than our current index, or the array at our current index, +1, if that is also or that's greater than our current index, well, then we need to keep looking, right? And what is our case for reassignment of our pointers? Well, we're going to look at our first index, and we're going to ask if that current index, is it greater than where our current place in the array? If it is, then we know that we can ignore all the numbers to our right. So we will reassign high to be equal to our midpoint. If that's not the case, then we'll reassign low to be equal to our midpoint. And then we need to reassign mid to be the midpoint of these new values. So we'll combine our high and our low, and we'll divide it by 2. And then after that, we just want to return the midpoint. So that takes care of finding our peak. And now we just need to do our binary search. So again, we'll define a midpoint, and we'll say equal to the floor of combining our high and our low and dividing it by 2. And what's our looping condition here? Well, while our current point, so the current midpoint, while it does not equal the target, and we also, if the distance between our high and our low, if the distance between our high and our low is greater than 1, then we also want to keep looking. So we'll just, to be safe, we'll say math.abs of high minus low. If that is greater than 1, well, then we also want to keep looking. And so now we need to, what's our case for reassignment here? So we want to look at our current point, and we just want to see if it is greater than our target. If the current point we're on is greater than our target, well, then we know we can ignore all of the answers to our right. So we can reassign high to be our midpoint. Otherwise, if that's not the case, then we can reassign low to be our midpoint. And then we just need to reassign mid to be the midpoint of our new values. So high plus our low divided by 2. Okay. So, and at the end here, well, we just want to double check to make sure that the midpoint that we're going to be returning at the end of this, we just want to make sure it's equal to our target. If it is, then we'll return that midpoint. If it's not, then that means we have terminated our search and we haven't found the target. So we'll return -1. Okay, so just to do a little recap, our search function here, we're first finding the peak, and then we're checking to see what side of the array do we need to do our binary search on. If our target is greater than the value in the first index of our array, well, then our answer lies to the left of our peak. If that's not true, then the answer lies to the right of our peak. Then we wrote a function for basically finding the max value or the peak in the array. So while our current place in the array is not greater than both the value on its left and its right, we're going to keep looping. And we'll just do our reassignment. And we'll say if the current place in our array, if it is greater, if it's not greater, or if it is greater than the first, or if it's less than the first index in our array, well, then our answer lies to the right of our peak. If it's not, then the answer lies to the left. And then we just reassign our midpoint and return that midpoint. And then likewise with our binary search, it's a very similar function, except our looping case is that it does not equal the target, or the distance between our two search points is less than is less than 2. And then if we haven't found our target yet, if we're too high, then we'll reassign our high point, our midpoint to be our high pointer. Otherwise, we'll reassign our low pointer to be the midpoint. And then we'll just recalculate the mid and return that at the end. If the midpoint that we're returning equals the target, well, then we'll return that midpoint. Otherwise, that means we didn't find an answer, so we'll return -1. Okay, let's see how we did. Okay, great. So like I said before, LeetCode has a conspiracy against me. They don't like that I'm doing all these videos, and they're making it look like all of the runtimes for my problems are terrible. So I'm going to keep doing what I've been doing to actually test my code, and I'm just going to rip the best solution ever to grace the presence of LeetCode and run it against my code and just see how well we did. So we will grab this answer here, the best possible solution on LeetCode. And we'll go back to our code. And we'll paste this in here. And let's see how we did. Okay, great. We got the same runtime as the best solution on LeetCode once again. So we can all pat ourselves on the back and feel good about what we did. But what I think is one of the coolest things about this problem, what I really like about this problem, is it forces you to do binary search in kind of a little more unorthodox way. So anytime you can isolate an answer, and you can figure out a way to know when you're on the left side of your answer or you're on the right side of your answer, well, you can do binary search. And this problem was a really great example of that, of finding our peak value, identifying like the unique ending case for that value, and then being able to implement binary search just by figuring out what side of my answer am I on. And then we can eliminate all the answers to the left or the right, right? So I think this is an important kind of lesson to learn. Maybe there's a way that we can isolate our answer, figure out where we are at every iteration, and eliminate half our search space. Anyway, I hope you enjoyed the problem. I hope you learned something, and I hope to see you in the next one.